Don't forget to subscribe and ring that bell.
There you are. Welcome to this request. I had several people request the 2015 free response question section of the AP Calculus AB exam. And no doubt you are all in the same class and you all had the same assignment. I don't know, maybe not. But you know what? I'm going to do it. I'm going to do it because one of the guys that left a comment requesting this mentioned to me, Visca, just like you like graphs and charts and table and your favorite color is green, can you please do this? And you know what? That tells me he actually watches and he actually listens. Maybe it's a she, maybe it's a they. I don't judge. I just think it's cool that they want to know math and they actually took a little bit of time out to learn a little bit about me. All right, so let's start. For your response, question number one, we get a graphing calculator. That's what I'm talking about. Let's go. So problem one reads, the rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is 20 sine of t squared over 35 cubic feet per hour. T is measured in hours, and t is in between 0 and 8 inclusively. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by dt, which is negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour for time between 0 and 8 inclusive. There are 30 cubic feet of water in the pipe at time equals 0. All right, that's a good thing to know. Let's just say this. At time 0, we already have 30 cubic feet of water in the pipe. That will come into play at some point in this problem. A states, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? If they give us a rate, this R of t is the rate of water going into the pipe. Okay, that's in cubic feet per hour. And we just want cubic feet. We are going to go backward. And that means we're going to integrate. All right. And they give us two bounds here from 0 to 8. So all I've got to do here, and this is really easy, especially with the calculator, is I'm going to integrate r of t dt. Don't forget your dummy variable. They will take points off from 0 to 8. All right, and I'm going to put that right in the calculator. So here we go. Let's start this, turn this on, and we are going to go math. 9 is my integration from 0 to 8, and I'm just going to put r of t into the integral. So we have 20 times the sine. We'll create a fraction here. We're going to use x instead of t, x squared, over 35. I'm going to close off that parenthesis, include my dummy variable, and my answer is 76.570. So that is approximately 76.570. You don't have to put cubic feet. It's not telling you to put a label. So we will just leave it like that. And 1A is done. 1B. Is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. Well, if we know that the water going in is at this rate, r of t, and the water going out, draining out, is d of t, okay, those are already rates. So when it asks us if it's increasing or decreasing, it's asking us if the amount, okay, if my cubic feet is increasing or decreasing. That means these are cubic feet per hour. And that's what R of t and D of t are labeled as, cubic feet per hour. So all I've literally got to do is find R of 3 and find D of 3 and find the difference. If it's a positive number, if there's more water going in than leaving, then it's increasing. If there is more water that is leaving than going in at time 3, then it would be decreasing. And the fact that we have a calculator makes this oh so easy. All right, let's find R of 3. So it is 20 times the sine. Create another fraction. X squared. Our x is 3. So it's 3 squared over 35. Pop that out. Bam. So the rate of water right at time 3 entering this pipe is 5.086. I've got to do the same thing for my D equation. All right. So I'm going to say negative 0.04. Now my x is 3, so it's 3 cubed plus 0.4. My x, or time in this case, is 3 squared. Oh boy, look at me go. You always got to make sure you don't make boo-boos like I am right here. Let's go. I left this all in the exponent like a dum-dum. Let's go. Pop off the exponent. Plus 0.4 times 3 squared plus 0.96 times 3. That gives us 5.4. All right, well, if we take the water coming in and subtract the water leaving the pipe or draining, we get negative 0.313. We'll raise that to a 4 because we're going to round 3 places. Negative 0.314. And we need to answer the question. It is decreasing. So let's state that. We'll say the amount of water, give a reason. It's decreasing. That's my answer. How come? Since, and you could just say R of 3 minus D of 3 is less than 0. I mean, but yeah, they don't say in the context of the problem. So I guess I could just go with that. I was going to write water is decreasing since it's draining 5.4 more than it's filling 5.086. But since R of 3 minus D of 3 is less than 0, it's negative. That's it. That's all that's required because it does not say in the context of the problem. We're good. 1C. At what time, t between 0 and 8 inclusive, is the amount of water in the pipe at a minimum? I feel like there was a problem on the 2019 or 2021 test where I kind of explained the same type of scenario. What I'm going to do, okay, what I'm going to do for part C is I'm going to graph these. Now we have a calculator. And what I'm going to do here is I will graph the water that's going in blue, and I'll graph the water that's draining in red. Okay, so let's just first start with that. Oh, great. I hope I don't mess up entering this in the calculator. So let me clear this. That's a lot. Let's go to y equals. And in blue, I'm going to have my 20 times the sine of a fraction which is x squared over 35. Close that parenthesis. And then, here we go, negative 0.04 x cubed, pop off the hat, plus 0.4 x squared plus 0.96 x. In my window, I only want from time 0 to 8. Why would I want anything else? So I'm going to graph this. Here's the water coming in. All right. And the red is the water leaving. Boom. That's good. Oh my. Let's look a little higher because we have to go to the number 8, right? Ooh, can I not do that on the screen here? I can't. 8 is right here. Okay, so I want to see higher up on the graph just for poops and giggles. So let's change our y. Let's start at 0 and we will go up to, I don't know, 30 by 10s. Okay, so again, there's the water coming in. That's not going to reach 30. That's good. And here's the water going out. Boom. There you go. Okay, this is good. So I'm going to focus. All right. I'm going to focus. There you go. Now it does it. I'm going to focus on the following. The red. Ooh, I get to use the highlighter? No way. The red is the water leaving. Okay. The blue is the water that's coming in. As long as the red is on top, and let me state this, as long as the red, which is D of T, is on top of the blue, which is R of T, from the moment it starts until this point right here, I am draining water more than water is running into the pipe. So as long as that draining function is higher, I'm losing water. Okay. The minute the water coming in, the blue line, is above the red line, I'm gaining more water. Okay. So right here, I'm gaining water because the water running in R is bigger. Okay. Right here, in between, okay, I'm losing water. How come? Because I'm draining water faster because that red line is higher up on the graph. So all I really have to do is see, well, what's this point of intersection right here? Okay, what is that on the x-axis? So let's go back to our calculator. And we are going to go second, trace, and pick choice 5, which is intersect. And I've just got to get close to the point of intersection. I don't have to be right on it. And I'm going to hit enter 3 times. 1, 2, 3. And in the bottom part here, it's 3.272. All right, 3.272. That's the time where we are going to have, what do they say? The water is at a minimum. So on your paper, you're probably going to want to like sketch the graph. D of T kind of comes up, then curves down. And this one starts, R of T comes down, kind of comes up and does this fancy thing here. Here's R of T, here's D of T, and this right here is at 3 points. What do we say, 272? 272. That's where we have when time is 3.272. There you go. Justify your answer. I mean, there's no math work. There's no calculations. So if you want to write something because it makes you feel better, water begins at time 0, draining faster than entering the drain pipe. Okay, and I gotta up until time equals 3.272. And there you go. That might be justification, although I honestly believe the graph would be enough. You can also say that d of t is greater than r of t until this point, from the beginning until that point. Many ways to write it and many ways to do it. All right, I've really enjoyed this problem. And it's sad. It's sad that it's almost over. All right, here we go. The pipe can hold 50 cubic feet of water before overflowing. So for time greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Oh man, stop. Right, but do not solve an equation involving one or more integrals that gives the time W when the pipe begins to overflow. Okay, okay. So we know the moment the pipe hits 50 cubic feet, 50 cubic feet, it's full and it will now begin to overflow. All right. If we look at our graph, is that thing still up? You'll see that, let's do this here. Okay. You'll see that d of t is much higher. So the water is going to keep on getting more and more and more and more in there because the rates the water is entering the pipe. Okay, I got this graph from 1C in case you didn't watch 1C. The blue line is R of t, the water coming in, and the red line is D of t, the water coming out. You see how the blue line starts to become a lot higher above the red line? That means the rate of water entering is a lot higher than the rate of water leaving, so it's starting to fill. All right? So what I'm going to do, okay, if I want to find just cubic feet, these are rates, let's not forget. It's cubic feet per hour. I just want cubic feet, so I got to integrate. Okay, I'm going to integrate from 0 to the start to sometime W. I don't know what that is, but there's going to be some time there that when I take the water coming in and I subtract the water leaving, don't forget your dummy variable for the love of God. Okay? There's going to be some point W that I can put in that upper bound to represent time. That the difference between the water coming in and water coming out, because there's more and more and more water coming in, will equal 50. Okay? Because once it gets at that point, it will begin to overflow because there's only 50 cubic feet of space in there for the water. But there's one thing. Do you remember when this problem first started? I don't know if you were here for this. Maybe, maybe not. We said that there are 30 cubic feet of water in the pipe at time 0. So I'm going to come back here. Okay? And I'm going to say, well, this didn't start at 0. I don't want this to be 50 because there's already 30 in there. So once this hits 20, I'm going to get to 50, won't it? So what I would do is I would take 30 plus whatever this is once that gets to 50. Because once this integral hits 20 plus my 30, then I'm going to hit my 50. They wanted an equation. They wanted an equation, so we need the equal sign. All right. So if we start with 30 and we add our integral, remember the integral goes from cubic feet per hour to just cubic feet, what they're looking for, of the water coming in minus the water coming out. Okay. to sometime W. Once that combined with 30 equals 50, it'll start to overflow. You don't have to solve for W. They want you to put W in for time for the upper bound. That's the beauty of this whole problem. We're done, and I'll see you for problem number 2. Bye-bye.
Don't forget to subscribe and ring that bell.